So let us summarize all the equations. What is the first relation that we have derived? Current I equal to closed surface integral of J bar dot ds bar. This is the first relation that we derived. Second relation is the relation between current density J bar and rho v. J bar is equal to rho v into velocity of the particles v bar. Okay. Next continuity equation is I equal to minus dq by dt, that is equal to integral form, that is J bar dot ds bar. This is the continuity equation. Continuity equation in integral form. Continuity equation in integral form, and we also derived continuity equation in point form, that is del dot j bar is equal to minus dou rho v by dou t. This is the continuity equation in point form or differential form. So these are the relations that you should remember throughout this electromagnetic field theory subject. Okay, what is the first relation? I equal to integral J bar dot ds bar. Next, what is the relation between current density and rho v? J bar is equal to rho v into v bar. Next, continuity equation in integral form is I equal to minus dq by dt, that is integral J bar dot ds bar. Continuity equation in integral form, and continuity equation in point form or differential form is del dot j bar is equal to minus dou rho v by dou t. Okay. Next, suppose if we take steady current, steady current means the current which does not vary with respect to time. Suppose if we take steady current which will not vary with respect to time, that means dou rho v by dou t is equal to 0, because steady means it is always constant. For a constant, if you derivate, what will happen to dou rho v by dou t? Dou rho v by dou t will become equal to 0. So for steady currents, del dot j bar will become equal to 0. This is the final relation for steady currents. For general currents, del dot j bar is minus dou rho v by dou t. That is the continuity equation in point form or differential form. Then the continuity equation in integral form is I equal to minus dq by dt, that is equal to closed integral of j bar dot ds bar. So these are the relations that we have derived until now. Next, we should go for what is meant by a conductor and how the current will flow in a conductor. Here again we will shift to the concept drift current. Then we will derive some relations again. Okay. Now we are entering into the topic conductors. So actually this unit is behavior of conductors and dielectrics only. So behavior of conductors means, see what is meant by a conductor basically, that material which allows the free flow of electrons is called as conductor. That means there will be number of free electrons that are available in your conductor. Whenever you are applying some voltage, then what will happen? See, again I am repeating, a conductor is nothing but a material which allows the free flow of current or free flow of electrons. General electric current we are referring. That material which allows the free flow of current or electrons is called as conductor, that we are studying from our childhood. So in that conductor there will be number of free electrons. Okay, there will be number of free electrons. Suppose if you apply, see I am taking a conductor like this, some conducting material like copper or aluminum or anything. If I am taking a conductor, there will be number of free electrons. There will be number of free electrons that are available in this conductor. Now they will not move until you give some electric voltage or potential. Suppose if you apply some electric voltage or potential If I apply some voltage or potential, what is the conventional direction of current? Conventional direction of current is opposite to the flow of electrons. Okay. Conventional direction of current is opposite to the flow of electrons. Your electrons will move in this direction. Your electrons will move in this direction and your protons will move in this direction from high potential to low potential. Now, previously, before giving this electric potential or voltage, these charges are, these free electrons are randomly distributed. That means in different spaces, in different places they will be spaced. On the application of this electric voltage or potential to this conductor, now these free electrons will start moving in different directions. On the immediate application of this electric voltage or potential, these electrons, these free electrons in the conductor will start moving in random direction and they will start colliding with the other atoms. These electrons will move, these free electrons will move in random directions, and collide with other atoms. Okay. Now, on the application of this voltage or electric potential, electrons will move in random directions and collide with other atoms. Okay. Now, that will not happen for a long time. After some time, these electrons will gain, these free electrons will gain a constant velocity. These free electrons will gain a constant velocity called as drift velocity. These free electrons will gain a constant velocity called as drift velocity Vd. As velocity is a vector component, that is denoted as Vd bar. Okay. See, again I am repeating. In conductors, there will be number of free electrons. When you apply some electric voltage or potential, those free electrons will start moving in random direction. They will collide with each other. They will collide with other atoms also. That process will not happen for a long time. Just after some time, those electrons will gain some constant velocity called as drift velocity. So after gaining the drift velocity, now you can obtain drift current. Already we have defined in our starting lecture that the current that is flowing in a conductor due to drifting of electrons is called as drift current. Now these electrons, after gaining the drift velocity, will start moving. That is called as drift current. Okay. Now these electrons are moving with a constant velocity called as drift velocity. Your direction of electric field is also in the direction of the current that is flowing, conventional current. Okay. The electric field E bar will be also matching with the direction of conventional current I. But the direction of electrons is opposite to the electric field. You can observe electrons are flowing like this. Conventional current is flowing in opposite direction. Your electric field E bar will be matching with the conventional current direction, but electrons will be moving in opposite direction. Now, these electrons are moving with drift velocity Vd, and if you apply more electric field, then you will get more velocity of the electrons. That means Vd and E are proportional to each other. Vd and E are proportional to each other, and if you remove that proportionality, you will get a constant called mu. So Vd bar is equal to minus mu E into E bar. Vd bar is equal to minus mu E into E bar, where this mu is called as mobility of the particles. That means here mobility of the electrons, where that mobility is given by velocity by field. Velocity by field. Velocity is expressed in meters per second and field is expressed in volts per meter. So finally your unit is meter square by volt second. Okay. So here how much of electric field you are applying, that much of velocity you are getting. If you apply more electric field, the velocity, drift velocity of the electrons is more. If you apply less electric field, drift velocity of the electrons is less. So both are directly proportional. If you remove that proportionality, you will get a constant called as mu e. Vd bar is equal to mu e into E bar. This is the drift velocity of the electrons, and mu is the mobility of the electrons. That's why it is denoted as mu e, which is given as velocity of that moving electrons divided by the electric field. So velocity is expressed in meters per second and field is expressed in volts per meter. Meter square per volt second is the unit of this mobility of the electrons. And why we have kept this minus sign means we can observe that the flow of electrons is opposite to the flow of the conventional current or the applied electric field. So the electron direction is opposite to the electric field. Opposite, that's why we have kept minus sign. So this is the relation between drift velocity Vd bar and the applied electric field E bar. Okay. Now, if you generalize this, in the place of J bar, what you can substitute? J bar is equal to rho V into V bar, where V is the velocity. Here you are having velocity. Okay. If you take this expression, use this expression, we know that current density J bar is equal to rho V into velocity V bar. Here the velocity is drift velocity. So in the place of V you can substitute minus mu E into E bar. So rho V. In the place of V bar, what I am substituting? Minus mu E into E bar. And as we are not considering entire volume of the body, I am considering only the flow of electrons in this. So the charge density is generally considered only for electrons because I am concentrating on electrons here. So I can take J bar is equal to minus rho E into mu E into E bar. Okay, J bar equal to minus rho E into mu E into E bar. Keep this relation aside. Next, using this relation, we can go for Ohm's law again. So here we are using the relation J bar is equal to rho V into V bar. So I am substituting in the place of V, what I am substituting? Vd bar. So in the place of rho V, instead of taking entire volume of the body, the charge density rho V can be replaced with charge density rho E because I am concentrating only on the electrons. That's why I am concentrating on the charge density of electrons only. And in the place of general velocity V bar, I am substituting the drift velocity of the electrons Vd bar. So Vd bar. So I can also write J bar is equal to rho E into Vd bar. This is another relation while you consider the drift current in the case of conductors. So general relation is J bar equal to rho V into V bar. Only for drift current in the conductors, J bar equal to rho E into Vd bar. Now if I substitute Vd bar equal to minus mu E into E bar in this, I can write J bar equal to minus rho E into mu E into E bar. Now this relation is further extended to a concept called point form of Ohm's law. Point form of Ohm's law, which is very important. So already we obtained the relation J bar equal to minus rho E into mu E into E bar, where J bar is the current density of the conductor and E bar is the applied electric field intensity to that conductor. So in the place of this minus rho E into mu E, what is this rho E? Charge density of electrons, and mu E is the mobility of the electrons. Why we kept minus sign means here electrons are moving opposite to the electric field that you have applied, that we have seen previously. So in the place of this constant, I am writing some sigma. J bar equal to sigma E bar. This is the point form of Ohm's law, where this sigma is the conductivity of the material. Conductivity of the material, that means how much it is able to allow the current to flow through it. That means the ability of the conductor for allowing the current to flow through it. That is the conductivity of the material, which is expressed in mho per meter or Siemens per meter. Okay, J bar is equal to sigma into E bar. This is the point form of Ohm's law, which you should remember very well. This is useful for your competitive exams also, where sigma is equal to minus rho E into mu E. Sigma is the conductivity of the material, that is mho per meter or Siemens per meter, and this equation J bar equal to sigma E bar is the point form of Ohm's law. Point form of Ohm's law, which is very important relation. Now, as the temperature increases, your conductivity decreases. Remember this statement: as the temperature increases, your conductivity decreases and resistivity increases. That means for these conductors, as the temperature increases, conductivity decreases and resistivity increases. What is the point form of Ohm's law? J bar equal to sigma E bar. Okay. So what is the other relation that we obtain? J bar equal to sigma E bar. This is the point form of Ohm's law, where sigma is equal to minus rho E into mu E.